Hello, welcome to this video on mesh and nodal analysis. I will give a couple of examples on these two methods, and I will try to illustrate the basic procedure, and we'll show you how you can calculate the different branch currents and so on using the results that you will get from these two analyses here. Okay, first we have this example. We have a circuit. It has a number of sources, and would like to apply mesh analysis to calculate the current I, this current here flowing in this 1 kilo ohm resistor. So it's very important to note the polarity. The current is assumed to be pointing from top to bottom, so from bottom to top. And if your answer actually is flowing the other way around, your answer will be negative. So very important to pay attention to the sign here. Of course, in mesh analysis, and as we explained in classes, it's better to get rid of all the current sources that you have. Mesh analysis is done in an easier way if you have only voltage sources. This does not mean that it's mandatory to remove some of these sources. Some of them will not cause any problem, but let's make it a standard procedure. If you have a current source like this one in parallel with the resistance, it's better to replace them by one voltage source in series with the resistance. This, as you see, will simplify things a lot. So, as I mentioned in classes, do not start to do any mesh analysis or nodal analysis until you have simplified your circuit. So here we can see a number of simplifications that can be made just to make the equations way simpler. We have here three volts, and you have here 2 volts. Both of them are trying to push current in the same direction, so we can sum them into one voltage source of 5 volts. We have here 1.8 kilo ohm in series with 1 kilo ohm, in series 1.2 kilo ohm. These three resistances are in series, so I can replace them by just one resistance, which is equal to 1.8 plus 1 plus 1.2, so we have 4 kilo ohm. This will not affect the result in any way, and you get the same I in this branch. Now, we have also this 1 kilo ohm in series with these two here, but these two are in parallel, and as I mentioned in classes, do not get confused. This node is the same as this node. So the 2 kilo ohm in parallel with 2 kilo ohm will give you 1 kilo ohm. This 1 kilo ohm is in series with another 1 kilo ohm, so the total resistance of this branch is 2 kilo ohm. So the main things we're going to do for the next slide is simply sum these three resistances into one resistance, sum these two voltage sources into one voltage source, replace this current source into a voltage source in series with resistance. The value of this voltage source will be 1 milliampere by 1 kilo ohm, so it's 1 volt in series with 1 kilo ohm. And now we redraw the circuit again before we do any mesh analysis and see how the circuit now looks like. Okay, now so the circuit now looks much tidier. It looks much cleaner. We are now ready to do mesh analysis. But there is a question that there is a choice I had to make here. That this problem requires to calculate the current in the 2 kilo ohm. You can see here from this figure that this 2 kilo ohm coming from this current source is in parallel with this 2 kilo ohm. So I could combine them into one resistance of 1 kilo ohm, but the result is that this resistance through which the current I'm looking for will disappear. And then I have to do extra calculations towards the end to get that current. Okay, so I solved it using both approaches. So in the first case, I'm not gonna touch this one. Why? Because I'm looking for the current flowing here. So I will simply what I will do, I will convert this current source into a voltage source as we agreed in all mesh analyses, but when I will convert it, I will use only the 2 kilo ohm. So this will give me a voltage source in series with 2 kilo ohm. Okay, the value of the voltage source equal 2 milliampere multiplied by 2 kilo ohm. I'm not gonna touch this one. Why? I'm not gonna be touching it because simply the current I am looking for is going through it. This is one approach of solving it, and I will show another approach where we can simplify the circuit further. So now what I'm going to be doing, replace these between here and here, both a voltage source of value 4 in series with the resistance 2 kilo ohm. And notice, because this current is flowing from bottom to top, I will have to observe the polarity of the voltage source. The negative terminal of the battery will have to be in the bottom side. Now let's redraw the circuit and see how it looks like. Okay, because of my choice not to get rid of the 2 kilo ohm, I end up with 3 loops. Loop number 1, loop number 2, loop number 3. As in mesh analysis, every loop will have its own current. Okay, so this is a current flowing in loop 1, I2 is flowing in loop 2, and the I3 is flowing in loop 3. I did not remove this resistance, and as a result I ended up with 3 loops. I could have removed it and then I end up with 2 loops only, but this will require me extra work at the end. I will keep it that way and let's solve it and see what we're going to be getting. Of course, when you assume the polarity this way, this I1 will be flowing in this branch from bottom to top. So the polarity of the drop across the 4K will be with this one here. If I assume that I1 is greater than I2, the current flowing in the resistance 2 kilo ohm is flowing from top to bottom, and its value is I1 minus I2. Okay, so now we apply KVL. We go around this loop in the clockwise direction. Every time we move from negative to positive, we count it as a voltage increase. Every time we go from positive to negative, we count it as a voltage drop. So here let's apply KVL. I have 5 volts minus 4 multiplying I1. And here I'm not going to say 4K multiplying I1. I will write it as 4I1, and the I1 will be in milliampere. So I'll assume everything is in milliampere. Let's continue. So 5 minus 4I1. Here is positive, negative. So you have minus 20. Here positive, negative. You have minus 3I1 minus I2. So I assume this polarity here because I assume the I1 is greater than I2. So the net current is flowing from top to bottom. Of course, as my assumption is not correct, this drop will be negative and the polarity will be reversed. So here 5 minus 4I1 minus 20 minus 3I1 minus I2 is equal to 0. This is KVL for the first loop. We sum all the coefficients. So here we have 4 minus 4I1 minus 3I1 minus 7I1. I move it to the other side, I get 7I1. Here I have 3I2. I move it to the other side, I get minus 3I2. Here I have minus 20 plus 5, I get minus 15. So this is my first equation. And as I explained in class, it's very important to keep the parameters or your unknowns ordered. So you have I1, I2, and I3. So after every equation, you have to order them in, after you found all the coefficients, you have to order them in the order I1, I2, and I3. Now let's go around loop 2. So this is loop 2 here. This is current I2. I'll keep this polarity here. So I'll assume for this branch that I1 is still greater than I2. I2 is the only current flowing here and it's flowing from left to right. So it will create this drop here across the 1 kilo ohm. And I will assume in this branch, which is a common branch between loop 2 and loop 3, I'll assume that I2 is greater than I3. So the drop appearing across this 2 kilo ohm here will be positive, negative with a shown polarity. So let's now go around this loop and apply KVL. Again, if you move from negative to positive, it's considered voltage gain. If you move from positive to negative, it's considered voltage drop. So you have 3 multiplying I1 minus I2. Negative, positive, plus 20 minus 1 multiplying I2. Negative, positive, plus 1. Positive, negative, minus 2 multiplying I2 minus I3 is equal to 0. So this is the equation written for the second loop here. And as I said, I do KVL in a very systemic way. Negative, positive, it's a voltage increase. Positive, negative is a voltage drop. Now we do exactly the same thing. We collect all the coefficients and we have to do it in order. So I have 3I1 here. I move it to the other side, becomes minus 3I1. I have minus 3I2 minus I2 minus 2I2, so you get minus 6I2. Move it to the other side, you get 6I2. I have here plus 2I3. Move it to the other side, you get minus 2I3. Here we have 20 plus 1, you get 21. So this is the equation governing the second loop. I have three unknowns, I1, I2, and I3, then I have to get three equations. We go around this last loop here, which is a small loop, and then again, I'm gonna keep the same polarity here, positive, negative. So this assumes that I2 is getting I3. I3 is flowing in this branch, then the drop across this 2 kilo ohm here is positive in the top terminal, negative in the lower terminal. So let's go around this loop and apply KVL. Every time we cross negative, positive, we count it as positive. Every time we cross positive, negative, we count it as negative. So here you have 2, this one will be 2, this is this polarity assumed from the previous loop, 2 multiplying I2 minus I3. And then you have minus 2 I3, this is positive, negative. And you have this one is positive, negative, minus 4 is equal to 0. So this is the equation that we have for loop 3. Again, you sum all the coefficients and then you take into account the order. You have to be ordered, I1, I2, and I3. Here the coefficient of I1 is 0, so don't have to worry about that. So you have here 2I2, it moves to the other side, minus 2I2. You have minus 2I3, minus 2I3, move the other side, 4I3, minus 4 is still there. So these are the three equations for I1, I2, and I3. This really will end the KVL part or the circuit analysis part. What remains is the simply mathematical part. How do you solve this system of equations? Solving system of equations can be done through determinants. You can use your calculators as I explained in the video I talked about earlier. Or you can try to substitute from one equation to the other. But the easiest way in an exam is simply to use your calculator, because as I mentioned, we simply want to see that you know how to use circuit analysis, but the calculations of the matrices themselves can be done using the calculator. Okay, let's move the next slide and see how we can solve these three equations in three unknowns. Okay, we write this system of equations in the form of a matrix. So here we have the first equation, 7I1 minus 3I2 plus 0I3 is equal to minus 15. Second equation, minus 3I1 plus 6I2 minus 2I3 is equal to 21. Third equation, 0I1 minus 2I2 plus 4I3 is equal to minus 4. So this system has the form AI equal to B, where I is the vector of unknowns I'm looking for, I1, I2, and I3. A is the matrix of coefficients, and B is the right-hand side vector. I explained in class how to solve this using determinant. So first you have to find the determinant of this matrix A. And again, it is 7 multiplying 24 minus 4 plus 3 multiplying minus 12. And this one will give us 0. This will give you 104. And then we create a matrix called A1, where we get rid of the first column of the matrix A and replace it by the right-hand side. So we end up with this matrix A1 here. So you can see this column here, this first column, is the right-hand side, while the other two columns are coming from the matrix A. So find the determinant of this matrix A1, it's minus 72. This means that I1 is a determinant of A1 divided by determinant of A. So you get minus 0.6923. Now, you create another matrix called A2. A2 is the same as A, but this column here, this second column, will be replaced by minus 15, 21, and minus 4. And if you do that, you will get the determinant of the matrix A2, 352. This means that the current I2, 352 divided by 104. The determinant of A2 over the determinant of A. This will give you 3.3846. And then the last one, we build a matrix called the A3. It is identical to this matrix, except that we get rid of the third column and then replace it by this vector here. So it's going to be 7 minus 3 minus 15 minus 3, 6, 21, 0, minus 2, and minus 4. And then get the determinant of this matrix A3, it's equal to 72, and you get again the value of I3. So now we have solved for all loop currents. Then we know the currents everywhere in the circuit. Why? Because every branch is either owned by just one loop or it is shared between two loops. If it is shared between two loops, then we subtract their two currents. If it is only owned by one loop, then the current of the loop is the one flowing in that branch. Okay, so let's go back again. Before we did the simplification, This was the 1 kilo ohm, and we had 2 kilo ohm, 2 kilo ohm. This is the second loop, this is the third loop. So the current I flowing here, as you can see from this figure, is nothing but I3 minus I2, and this I3 minus I2 because if you assume direction of the current I. Okay, so remember this is here to the right is the third loop, this is here to the left is my second loop, and this is the 1 kilo ohm in series with another 1 kilo ohm which is equal to 2 kilo ohm. I'm just showing you how it looks like in the original circuit. So this means that the current I'm looking for, which is flowing in the 1 kilo ohm resistor, is nothing but I3 minus I2. So this is 0.6923 minus 3.3846. It gives you minus 2.26922 milliampere. So in this way, as I explained earlier, I kept the same resistance. I kept this 2 kilo ohm. I did not touch it. I did not remove it when I simplified the circuit. Let me show you another approach in solving this problem that will yield exactly the very same answer. Okay, so here we have the same circuit, the very same circuit. I still have this current source. I have the 2 kilo ohm. I have the 2 kilo ohm. In my initial analysis I did not touch this resistance because I thought it would be easy to do it that way. Now I'm gonna combine these two into one resistance, and then you have a current source of value 2 milliampere in parallel with a resistance of 1 kilo ohm. So I can replace it by a voltage source of value 2 volts in parallel with a series resistance of 1 kilo ohm. So between here and here, between this point and this point, I connected one voltage source and one resistance. But this resistance here is 1 kilo ohm, which is a parallel combination of 2K and 2K. What I did now, I did absorb this resistance into this resistance here. This will require me, after I calculate the current I2, to do a little bit more work. Okay, and I will show you how we're going to do that. But this simplified the circuit because now I don't have 3 loops anymore. I have only 2 loops, and I have a current I1 and a current I2. So only 2 unknowns in this circuit. It's a little bit simpler. Okay, so now we will consider this circuit here, and we'll apply KVL to solve for I1 and I2. Remember, I1 did not change from the original circuit. So let's see how we can write the equations here in this new circuit here. Okay, we apply KVL in the same way we explained earlier. We have two currents, I1 and I2, and they are flowing in loop number 1, loop number 2. So this is I1 is flowing this way, okay? And you have I2 is flowing that way. We'll follow exactly the same procedure we explained earlier. We'll apply KVL around this loop, and every time we move from negative to positive, we'll count it as a positive, as a voltage gain. From positive to negative, we count as a voltage drop. Because this current is flowing this way, is going from bottom to top, the polarity across the 4 kilo ohm is positive, negative. And in this branch, we'll assume that I1 is greater than I2. And in this case, the drop across this 3 kilo ohm is positive, negative. Okay? So now we can go around the right KVL. You have 5 minus 4I1 minus 20 minus 3 multiplying I1 minus I2 is equal to 0. This is the same equation we got in the first approach. It's here, it's shown here, okay? Now now we have a different loop, and the second loop is a little bit different. So again, we'll go around. I'm not going to change this polarity here. So I'll assume that I1 is greater than I2. Here the I2 is flowing from left to right, so this is positive, negative. And here is flowing from top to bottom, so it's positive, negative this way. So let's apply KVL. You have 3 multiplying I1 minus I2 plus 20 minus 1 multiplying I1 plus 1 minus 1 multiplying this I2 here minus 2 is equal to 0. Let me repeat this again. So you have here 3 multiplying I1 minus I2 plus 20 minus 1 multiplying I2 plus 1 minus 1 multiplying I2 minus 2 is equal to 0. Okay, so this is here, this is the equation of the second loop. Again, we'll collect all the coefficients of I1, I2, and so on, and then we have to put them in order. I'm stressing this again because this can cause trouble if you're not paying attention. Your matrix A will be wrong, and then when you try to solve it using a determinant, using a calculator, you end up with wrong answer. So you have to keep always the coefficients in the form I1, I2, and I3. They have to be in order. This is the first equation, and if you simplify this one, this is the second equation. If you solve this using determinant, if you solve it using your matrix, whatever, you end up with this answer here. This is I1, this is I2. I1 is the same one we got in the first technique. I2 changed a little bit, okay? Now we have to go back again and ask ourselves how we can get the current flowing in the 2 kilo ohm resistor, or the resistance we had over there, which is, I think it was 1 kilo ohm. Remember, this 1 kilo ohm is absorbed here. But this current I2 that we solved for is the current flowing in this resistance here, in this 1 kilo ohm resistor. So I'm gonna redraw the circuit again before I removed my source, and then I try to solve for the current I'm looking for. So this is how the circuit looked like. We have a current 2 milliampere in parallel with a 2 kilo ohm, and we already solved for this current I2. We know what's I2. We know what's I2 right now. I2 is this current flowing in the 1 kilo ohm resistor, because this branch is only associated with the second loop. So I have now a current source flowing in, I have another current flowing in, and I have two equal resistances. So this looks like a current divider. So half of the current will flow in this 2 kilo ohm, half of the current flow this. So what is the current flowing in these two resistances? It's 2 milliampere plus this current. So from KCL, these two currents, this one here and this one here, they are flowing into this node. Okay, this is one node here, and this current is flowing. This node will split equally between 2 kilo ohm here and 2 kilo ohm here. So you can simply say that the current I am looking for is nothing but this current I2 plus 2 milliampere, and then I divide it by 1/2, and then I give it a negative sign because of the polarity. This sum here between this one and this one will result in a current flowing from top to bottom, while I is flowing from bottom to top. So this is the expression here for the current I. I is minus is I2 3.384. This is 2 milliampere, and then you divide by 2. You get exactly the same answer that you got before. Okay? So, but the only difference here is that after I got my answer from using mesh analysis, I had to go back and do some extra work, because this resistance was absorbed into this one, and we end up with only 1 kilo ohm resistor. Okay? But the procedure yields exactly the same answer. It is saying that I is flowing from top to bottom, and its value is 2.6922 milliampere. Okay? Also, one thing I'd like to stress, when I did KVL, when I multiplied 2 kilo ohms, say, by resistance, by the current, I didn't say 2 kilo ohm multiplied by I. I said 2I. Why? Because I'm assuming that current is in milliampere. So whatever answer I'm going to be getting, I'm counting it automatically as a milliampere current. Okay, let's move to another example. This example here is required to solve this circuit using nodal analysis. I would like to find the voltages VA, and you have here, this is actually A, not B. So let me correct this one here in the notes. This is here is VA. Okay, so can count this one as VA, and the voltage VB here. Okay, and this is a circuit that has voltage sources, has current sources. As I explained in class, nodal analysis prefers current sources, not voltage sources. Not all voltage sources are going to cause trouble. Some of them can, and we have to use something called the super nodes. And we did not talk about this, but anyone who's interested can try to research it. But for this one, I'm gonna get rid of this voltage source. I have a voltage source in series with a resistance, so I'm gonna replace it between here and here by one current source in parallel with the resistance. The value of this current source is 3 divided by 2, so it's 1.5 ampere. It's series with a 2 ohm resistor. Okay. I have also here 3 ohm in series with 2 ohm. I can put them as 1.5 ohm resistor. I have 2 ohm in parallel with 2 ohm. So I can combine these two into 1 ohm resistor just to simplify the circuit before I do nodal analysis. This will make the circuit look tidier. I have less branches, I have less components, I'm less susceptible to errors, okay? So let's redraw the circuit after we got rid of this voltage source here. So between this point and this point here, I'm gonna have a current source in parallel with a resistor. The resistor is 2 ohm and the current source is 1.5 ampere. 3 divided by 2. Okay, let's draw the circuit again and see how it looks like. Okay, so this is we got rid of the voltage source. This is now the new current source and its parallel resistance, and this is 5 ohm in parallel. I did not combine them. I could have combined 5 ohm in parallel with 2 ohm, but I kept them as they are. I combined 2 ohm in parallel with 2 ohm. I replaced them by 1 ohm. So now we are ready to apply nodal analysis. Nodal analysis is simply saying that you apply KCL at all the independent nodes that you have. Remember, we have in this circuit one node, a second node, and then a third node. These two here, this one and this one, they are one node. Okay, so don't be confused. This one, this one, this one, this one, and this one, they are all one node. This is the ground node. Okay, so we have here only two nodes. This one here, and this one here. And I can define the voltage V1, the voltage of this node relative to ground, to be V1. The voltage of this node relative to ground to be V2. And now we start to apply KCL at this node, at node number 1 and node number 2. KCL has three ways of writing it. You can say the sum of the currents flowing into the node is equal to the sum of the currents flowing out from the node. So this is the one I'm going to apply here. I have one current flowing in, okay? And I will assume that V1 is positive, and if V1 is positive, there is a current flowing between here to ground. If I assume V1 is higher than V2, there is a current flowing from here from left to right. There is a current flowing here from left to right. Okay, so I could see I have only one current flowing in. I have a current source flowing out. I have this current flowing out, and this current here is V1 minus 0 divided by 1. I have this current flowing out, but this current is V1 minus V2 over 2. I have this current flowing out. This current is V1 minus V2 over 5. Notice these are all one node, okay? Don't get confused. These are one node. So one current flowing in, 1, 2, 3, 4 flowing out. There are total of 5 branches connected to that node. One current flowing in is equal to 4 currents flowing out. So this is 2 ampere flowing in is equal to V1 over 1, we have this term here, plus 1.5, we have this term here, plus V1 minus V2 over 2, we have this term here, plus V1 minus V2 over 5, we have this term here. What remained is simply to collect all the coefficients of V1 and V2 and put them together. So 1.5 minus 2 and minus 1.5 will give you 0.5. You have here V1, you have half, so 1.5 V1, and then you have another 0.2, you get 1.7 V1. You get here minus half V2, and you have minus another point, you have another here, another term here related to 0.2. So let me correct this one here. So here you have, I have two terms having V2. So this one is 1/2 V2, and this one is 0.2 V2, correct? So I can simply, this here has to be 0.7. This one is written the wrong way. This should be here 0.7 V2. Okay. Anyway, you can simplify this equation, and you can probably have this one not correct as well. So you can divide as 7 here. So this will be 7 V2. Okay. It's very easy to make mistakes here in these formulas, or not, unless you are paying attention. Now we move to talk about the second node. This is the second node that we have here. Again, we are going to apply KCL. So I'm going to state exactly the same rule. Sum of the currents flowing in is equal to sum of the currents flowing out. I have one current flowing in here. I have one current flowing in here. Okay? And so both of them are flowing into the node. Okay? And I'm assuming that V2 is going to be positive. So this means that the current flowing in this branch will be flowing from this point to ground. So because V2 is higher than 0. And I will assume that we still have these currents in the same direction. I'm not going to change this direction here. So the currents flowing here, I'll keep them in this polarity. The currents flowing this way, I'll keep in this polarity. So these two are also flowing in. These are also flowing into this node. Well, so if we try to write the equation, let's write it. We can say, actually, we can write it in a different way. We can simply say that these two are flowing in, and everything here is flowing out. Okay, we can have these three things flowing out as well. So 1 plus 1.5 is equal to V2 over 8 plus V2 minus V1 over 2 plus V2 minus V1 over 5. So it's again, we can keep them this way and keep this current this way and then write them as currents flowing in, or I can simply write them as V2 minus V1 over 2 and V2 minus V1 over 5, and in that case they are flowing out. I actually have to be careful when I do that. So if I take a look at this equation, I counted that the two current sources are flowing in and the rest is flowing out. So I have here also a polarity mistake here. This has to be V2 minus V1. Okay, because if I'm gonna write it as V2 minus V1, it has to be flowing out. It has to be pointing this way. It has to be flowing from V2 to V1. Okay, we can now simplify this equation the same way, and please double check my answer. There are always a possibility of having a mistake here or there. And we end up with a system of two equations, two unknowns, and then we can solve for them. Okay, to clarify then for the second node, what we did is that we assumed there are only two currents flowing in, which is 1 ampere and 1.5 ampere, and there are three currents flowing out, V2 over 8 this way, V2 minus V1 over 2 this way, V2 minus V1 over 5 this way. Okay, and again, it doesn't matter if you have considered this current flowing from left to right for the first node and then from right to left in the second node, because this is the only difference here. This means you multiply the second equation by a negative sign, and multiplying an equation by a negative sign does not affect the solution of a system of equations. Okay, so now we have two equations. We take this equation, we simplify. The coefficient of V2 will be 1 over 8 and then 1/2 and then 1 over 5. So this is 0.2 plus 0.5. This will give you 0.7, and then 0.125. We end up by 0.825. The coefficient of V1 is equal to minus 1/2 and then minus 0.2. So we give you minus 0.7 V1. So now let's organize this and see how we can solve this system. Okay, so these are the equation we had from the previous slide. Okay, we're gonna now multiply both sides by 10 just to make the numbers a little bit nicer, and then again I'm warning you again one more time, you have to make the variables in order. So for the first equation it was V1 V2, second equation has V1 V2. Otherwise, when you put in your calculator, you end up putting a wrong matrix and getting a wrong answer. So now I reorganize them again. I wrote it this way. So my matrix A will have the first row minus 7, 8.25, the second row 17 and minus 7, while the right hand side is 25 and 5. So if I give this to my calculator or using the determinant method, any other method, I end up by VA is equal to V1. We're looking actually for VA, but VA is the same node as V1. It's 2.3699 volts. I end up with VB is equal to V2 is equal to 5.0411 volt. Please double check the numbers. There is always a possibility of having a mistake, but the procedure is in general correct. And the most important thing is to pay attention of your assumption, which currents are flowing in, which currents are flowing out, and then you apply KCL. The sum of all the currents flowing in is equal to the sum of all the currents flowing out.